changing the person. So maybe you were referring to a person with the same name, but it's actually another person. So there are these kinds of fields, some of which are more stable than others, but the ER model doesn't say explicitly how to treat them, but they exist. They say additional things on the entities, although the entities are identified by their IDs. Then entities are put in relationship with each other through relationships. Each relationship says that the entity that has a certain ID, called the primary key, is in relation with another identity that has another ID, its primary key. And these relationships have not only a list of people that put together, of entities that they bring together, they also have this thing called the cardinality. And the cardinality is used to express how many times a certain relationship may happen. So a person may have 0 or 1 or 2 or n different children. That's acceptable. And a child at the same time can have unlikely 0 parents or 1 parent or 2 parents or multiple parents if we accept a non-biological definition of the word parent in a certain moment. And that means that this relation is a so-called MN relationship, so it can change. And the same thing goes, for example, for the universities. But there are other relationships that are more fixed. When you come to the biological father, you have 1 biological father, and that's it. You cannot have 2. I hope genetics work like that. So the 95% of the ER model is displayed here, and this is all you need to know. There are entities, there are relationships, and they both may have fields. Now, that was a conceptual model that we have to turn into something that we can put in a computer. The thing that we can put in a computer is a relational model, the thing that your SQL database understands. And the translation, it's mostly one-to-one. If you have an entity, you turn that into a table. And the ID will be the ID field of the table. And all the fields that you had in that entity will be other columns in that table. And you see it here in the persons table. Usually the tables are written in plural. So the table names use the plural of the entity name. You see the persons table, it has an ID, and each person, so each row, has not only the ID, but also the additional field name. The same goes for the entity university. Then there are other tables that represent the relationships. And these tables, they use 2 different IDs. Sorry, they have 2 or more than 2 ID fields. And the content of these fields are just references to those other IDs. So this one here means if you want to know who is part of this relationship, go to the person table, find the ID number 1, and that person there, the one called Jack, is in relation with the university whose ID is 1, in this case, Bologna. And this person, for example, went to the University 1, Bologna, but also to the University 3, Oxford. Lucky person. Another person, person 2, only went to University 1, Bologna. So in this, when we translate the ER model into the relational model, we turn basically everything into tables, and then we associate special value to certain columns of those tables. As we said, we need this table thing is also, it's less abstract than the ER model that we have seen before, but is not yet concrete. In order to type it, we have to have a syntax for it. And that syntax is usually SQL. In SQL, you have various keywords that tells you how to create those tables and how to create those references. For example, here you see we create this table persons and we say the ID is the so-called primary key, the thing that identifies in a certain context that person, and that the relationship studied in references that ID under the name of the person ID. And with that, you can create very complicated, sophisticated models and turn them into databases that can be queried with SQL. Now, before we leave ER, I would like you to think for a second about the following thing. How can we know or understand if a certain entity that is stored as a person is also a parent? There is nowhere in this model the concept of a parent. However, we do have this concept of a parent. How do we make it happen? I can tell you that the ER model that we just wrote can express the concept of parent. However, none of these tables is called a parent. How can we use this concept? How can we introduce this concept in our model? And I would like, this is a real question, and I will wait a minute or so for an answer.
There was a child relationship, if I'm not wrong. So the person to which this relationship is referred is a parent.
Yeah, okay, that's, practically speaking, is the answer. And more conceptually, we can build on that by saying that in a ER model, there are certain concepts that are expressed as entities and certain concepts that are expressed as queries. So in order for the concept of parenthood to appear, we have to describe that as a query. This is what you just did. What you just did was stating in, not exactly SQL, but something that was understandable, the concept of parenthood. I call parents all the people that are in the person table that have at least one has-child relationship. We don't care about with whom they have that, but as long as they have one relationship, they are classified as parents. So the concept exists, it's just not expressed in a table. Tell me if you have understood that, because this is fundamental for the RDF and OWL part. Is that clear?
For me, it's okay.
Let's ask the negative question. Is there anybody that thinks that that's not clear?
No, everything is clear.
Okay, we're good to go. Then, goodbye ER. I told you, it was quick, it was small, it was easy. Let's have a look at RDF and RDF schema. So now I will talk, in this slide, and for the next 5 minutes, we will talk only about RDF, no RDF schema. However, when people usually say RDF, they mean RDF plus RDF schema. So keep that in mind. What I'm about to say only has to do with RDF alone, okay? RDF, the RDF meta model is demonstrably equivalent to ER. There is no difference, there is nothing that you can express in ER that you cannot express in RDF, and there is nothing that you can express in RDF that you cannot express in ER. So from that point of view, they are exactly the same thing. However, in the ER world, what you describe is are entities and the relationships within the entities. You do not talk about the instances. You assume that once you have created these tables, you will fill them with with instances. So you describe the concept of being a person, and then in your database you describe the single people, the single persons. In ER, that's twisted. In ER, you make statements, assertions about the reality as it is, and if you want, you can from that deduce the fact that there are certain classes that you call the entities, but the entities are real. In RDF, there are only real people. The group of entities that we collectively called people or persons emerges from the fact that we talked about single instances of people. The way in which you talk about instances in RDF is through this kind of assertion called a triple. A triple is what you see here. You have the first part of the triple is the subject, the second one is the predicate, and the third one is the object. So what you're saying is something else. For example, person 1 studied in Bologna. Person 1 has a child, person 5. Nowhere in these statements there is the concept of person. It's just identifiers and other identifiers. In RDF, the subject, the predicate, and the objects are just identifiers. We will see them more concretely in a second. And what you can do in RDF is just start saying what you want to say without first having to have those tables. So in the ER model, first you create the table and then you fill them with rows, with instances. In ER, you just say, okay, those are the rows, and you can understand them as a table if you spend a lot of time thinking about them. The ER model lends itself better, the RDF model lends itself better to the confused world of the web, in which you have many different actors that may not coordinate on a single table or on a single structure. So you say, look, this is what I know about this resource. I do not care if it fits your model or it does not. This is what I know. Again, I'm talking only about RDF without schema. Keep that in mind. So let's see some of these triples that we talked about. Let's concentrate on the very first line that you see here. It's broken, but it's a single line. This is a RDF assertion. As we said, there are only in RDF, everything is in a certain sense anonymous. There are only identifiers. The first line says that this specific thing identified by foo is in relationship with this other thing identified by thingo through a relationship identified by this URL. You consider all these URL just as strings, please. So you have this string, the entity referred to by this string is in relationship with the entity referred to by this string, and the relationship is identified by this. This is all very, very opaque. And in a certain sense, that's the point of RDF. If you think you're not understanding things, that's okay. It will be clear in a second. Because writing assertions in this way is extremely boring and repetitive, there are other syntaxes. For example, this is the N3 syntaxes that allows you to say, okay. Whenever I write, for example, EX, I mean this thing. So HTTP blah, 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 /foo can be simplified into EX:foo. So this first line and these two lines, they say exactly the same thing, that foo is in a relationship with Thingo, and the relationship is a rel relationship. But remember that you can mix and match all these things. So you can say that the foo is in a relationship with this arbitrary remote resource called booz that is hosted somewhere else. Now, things will be a bit clearer once we introduce schema. Schema, so up to now, all that we have done are stating accessions between something and something else, and say that the accession has this specific ID. With the introduction of RDF schema, what we can do is to say that certain resources all belong to a certain class, and we can also say that that a certain class is a subclass of another class, and that will imply that all the instances that are in a certain class are also instances of the superclass. And range domain that we'll see later. And RDF schema also has the concepts of resource. We can skip it for the second. So now we start seeing something that is more understandable. What we are saying here is that there is a resource called book, and this book is actually a class. So you see that this resource book is in relationship with the RDF schema resource called class through the RDF relationship called type. Now, this exception, it doesn't mean anything unless you, or better, the program that you're using, understand that RDF type means this is the type of this resource. And that a tool must also understand that RDF's class means now I am describing a class. So in order to have, in order for this book to really be a class, you need a program that understands RDF and RDF schema. That same program will also be able to understand that there is a resource called Divine Comedy that is a book and that is in relationship with the string Divina Commedia through the relationship has title, and is in relationship with this other resource that we identify by this URL, but that we do not know anything else about. We just know it's a URL, and we know that this entity is in a relationship with this other entity through the relationship called has author. In this way, what we have said is that there is a resource, and this resource has these properties. One of these properties is special, and is the property of being an instance of a specific class. Is this example sort of clear? Maybe not 100% clear, but can you follow along? Or should I spend more time describing this, explaining this? Okay, so either you are, okay, either it's clear or you are asleep. In both cases, I can go forth. And now there is a very important thing. The concept of domain and the concept of range. Properties, like for example, has title, have in RDF schema a domain and a range. This is something that is hidden in the ER model, but is very explicit in RDF schema and in OWL. The domain means that this property applies to certain kind of entities, namely those that are instances of a certain class. So has title can be used, or makes sense to use it, on entities that belong to the class of books. And this relationship is associates the book with a string, not with another kind of entity, but exactly with a string. And similarly for as author, the property author associates a book to a person as defined in the wiki prefix that is somewhere else. So what you are saying here is that whenever you see has author, like we did in the previous case, you can assume that this entity, of which in this moment you only know the ID, is a person according to the wiki definition, whatever that is. The concept of domain and range specification in RDF schema is very important because it allows the various programs to understand that this entity, even though it's just referred to by a string, can be assumed to be of a specific kind. And this allows the creation of very interesting networks and graphs. Another big difference with ER is that the subclasses or superclasses are in RDF schema explicit. You remember before we had this concept of the parenthood. A parent is in a certain sense a subclass of a person. A parent, all the parents are people, not all the people are parents. So the parent is a subclass of the person. We could not express that in a specific ER or RM terms, but we had a way to express it via a query. In schema, there is an explicit notation to say that, and it is the property subclass of. So there is a resource that is a class that is a subclass of another resource. You can see here that human is a subclass of animal, and dog is a subclass of animal, and male is a human, doggo is a dog. And now, if we are to query a RDF schema enabled database or data space or triple store, and we ask, is male of type animal, even though it's not written here, it should answer true. Going through male is a human is an animal, so male is an animal. This is possible only if this program does not only understand RDF, but also RDF schema. Please see that all these assertions are RDF assertions. But without the understanding of RDF schema, this assertion will not be true, because this assertion is not present here. Because it is not here, in the RDF world, it is not true. In the RDF plus RDF schema world, it is true, because it is deduced. And we will see the concept of deduce in a second. OWL. OWL is basically RDF schema with a couple of things removed for problems that have to do with the formalization, and expressed in many different ways so that you can create models that are even more faithful than the ER or RDF plus RDF schema models. OWL is much, much more powerful than the ER model. And with powerful, I mean it can express concepts and relationships that ER cannot express. However, in order, you remember this triangle, the more expressiveness you have, the slower your queries will be. And for this reason, Howl has many different variants. And you can say, I want to be very expressive and I accept that my queries will be very slow, or I can reduce my expressiveness to exactly what I need, and my reasoning will be faster. And most of the time, and that's funny, people choose things like EL or QL that are demonstrably equal to ER. So they express things in OWL because they look better, or because they match better the kind of technology stack that they have, but the expressivity of their model is exactly that of ER. Just to say again, don't discard ER too early. So OWL has basically the same kind of functionalities that RDF schema has, plus it introduces restriction and universal quantifiers. We will see them in a second. And the ability to negate things. In RDF and RDF schema, you can only assert the positive things. You can say that things exist or that something is a subclass of. You cannot say this is a subclass of the people of the people that have no children. That's not possible in RDF. There is no negation. However, you lose certain nice features like sequences or sets that are in RDF schema, but as I said, they cannot be expressed for theoretical reasons in OWL. An example of the extra expressivity that you get in OWL is the concept of parenthood. Now you can say that parent is the class that is equivalent to the class of all the things that have a property as child, and that as child as at least one person on the other side, because you also have a null as child property that says I have no children. So this is basically the formalization in OWL of what we said earlier. We define a parent as anybody who has a property as child that points to at least, sorry, that has at least one property as child that points to another person. And you can also have you can do other tricks and say, for example, that father is the intersections of man and parent. So a father is, so you can call father every entity that's parent and that is in the class man. It's a very, very expressive and nice language to use, even though the thing that you just saw cannot be used in the faster subsets of OWL. No, you heard me saying things like deducing or interpretation or reasoning. So, for example, in order to have a faster inferences or faster queries, you have to relinquish some functionalities. But what is exactly these things called the reasoning? As we said before, if I tell you that John has parent Jack and John has child Mel, can we, from these two assertions, also say that Mel has parent John? Answer?
No.
So you're saying that we cannot say that this is true. We cannot say that this is false, but we also cannot say that this is true. And that would be okay. Now, with the power of... so now we can add another assertion and say the relationship as parent is the inverse of the relationship as child. Now my question is, can we say that this is true?
Yes.
Yes.
The answer is Probably no. Why? Because this is a trick question. Because if you have just these, you do not have enough knowledge to say that. In addition to these statements, you need also the OWL semantics. As we said before, what you need is a program that not only reads those triples, it also has to understand that OWL colon inverse of has a very specific meaning. And that understanding that meaning means that when that program, here is the yellow thing, when the program takes your database and uses the OWL semantics on it, it can infer additional triples. For example, if it knows that S parent is the inverse of S child, then S child is also the inverse of S parent. This is a deduction that he can do because he knows the OWL semantics. Just by writing these, we cannot assert any of these new things. We need the OWL semantics in order to do that. And once you have that, you can combine these things with these other two things and derive this fifth statement. Mel has parent John. And now our query is trivially true. Yes, Mel has parent John. But in order to get to this point, we cannot just, so the truth of this statement is not in the database, is in the combination of the database together with the OWL semantics through a correct application or program. And this is something that is very, very important. This is also what is called the division of the business logic. There are certain things that may seem true by looking at the database that, however, are not true, because in order to be true, they have to be generated. And in order to be generated, there must be a program that knows how to generate them. And if you remember, I told you that there are certain profiles or subsets of OWL that have restrictions. And for example, in the EL subset, inverse of is a forbidden relationship. And that means that this database here, inside a program that only supports OWL EL, doesn't allow us to deduce that Mel has parent John. This deduction can only be said if we're using a program that uses a OWL semantics in which inverse of exists and has the meaning that we think it has. This is very, very important. Certain truths only exist if they are seen under the lens of certain semantics. And which semantics applies depends on the kind of meta model and OWL profile that you use. And as we said, the model that you use will be dictated by how fast you want your queries to be done. And just a practical note, the difference can be something between the results come back in 10 milliseconds versus the result come back in 10 minutes. It's this difference, milliseconds versus minutes. So now, very quickly.
Gioele?
Yeah.
We have a question in the chat about this.
There's a question in chat. So if we would add as child versus is parent, no answer. Nadine, can you ask that again, please? Maybe unmute yourself.
Yeah, I'm here with the others, so you can hear me, I hope.
Yes, I can hear you.
Okay. Without the OWL semantics, you would have also to add the inverse, has child inverse of parent of, and then the statement would have been true. That Mel has a parent John.
Okay, that's an interesting point. And the answer is no, it would not be true. So in art, it will not be true for two reasons. The first reason is, even though, so this thing derives from this thing, and this derivation is done by the alt semantic. So what you're suggesting is, okay, we can shortcut that, and we just write that. That it helps us a little bit, but it still doesn't help us, because this deduction here can be done once we know these two, but it's still a deduction that can be done only because we know these two. So in order to make this deduction, we need to know first the meaning of inverse of, and then we need to have these properties here, okay? So there are two things that we know, the knowledge and the presence. By just adding the presence, we have removed the part of the problem, but we haven't solved the whole problem because we haven't solved the part of the deduction. This is the thing, this deduction comes for free. So the addition comes for free if you have that deduction. So once you have the deduction, you have the addition for free, plus this other addition for free. And this was the first part of the problem. Then there is the second part. So you have to understand that in RDF, and OWL is RDF, plus extensions, in RDF, something is true only if it is in the database. That's very simple. The concept of truth in RDF is extremely simple. It is true if it is in the database. The fact is that the programs that support, for example, OWL, will take your database and add to this database all these extra statements, accessions that we said can be created. Which extra assertions will be created depends on the profile of the alt semantics. But the concept is always the same. The program will take your database and add many assertions to it, all the assertions that it can deduce. And then when the query will come, it will just check, does it exist or not? If it exists, it's true. If it doesn't exist, it is not true. And this is a very clear model, but it requires you to understand that before a query is made, all these extra assertions are generated by the semantics. And as you said, adding some of these statements will make some of these query truths, but you have to be very careful about which statements you add. For example, if you add the pair, if you add exactly that, then the answer will be true. But that's sort of a dumb thing. So you have added exactly the answer to your question. Why are you making the question?
Thank you.
Okay, you're welcome. Now, some models, very quickly in the last 10 minutes. What we are about to see are three models that either one has been done in RDF, one has been done outside RDF, and one has been done in OWL. And they all have the concept of person in addition to other stuff. So Foaf stands for friend of a friend, is a very old project whose aim is to model people and relation to other people. It's based on RDF. In a certain sense, it predates RDF, but the version that we use is RDF based. The official specification is expressed in OWL. But believe me when I tell you that the use of OWL is basically non-existing. You could do that in RDF plus RDF schema. It would be less elegant. It will work exactly the same way. Foaf is a very small model. It is very rough. It's not very sophisticated. What Foaf wants to do is to create very big networks of connections between people. For example, between people that have blogs or profiles in social networks. And they do that by saying, okay, I don't want to model the person a lot. I just want to model basic stuff, like as you say, that you have an account or a online gaming account if you are on, I don't know, on Steam, and that you have a family name or an account name. This kind of information that you have, that you need in order to express the fact that you have a profile somewhere on the web, plus other things that allow you to connect with other people. For example, the relationship knows or the membership class. Those properties allows you to say this person knows another person. And if you do that a lot, what you end up is a social graph. And all the field of studying social graphs come from here. This is an example of a Foaf person. You can see it's very basic, but it's also very understandable. It talks about James Wales, the founder of Wikimedia and MediaWiki. It says what his nickname is, and it has a relation to another person he knows, Angela Beasley. Okay, let's have a look at schema.org. Schema.org is an initiative basically by Yahoo and Google to make peace with the rest of the world and the ontology world. It explicitly does not use RDF or OWL. It can be expressed in RDF, but the specification doesn't use it. It is very ER-like, so there are entities and there are properties and everything. It's very well structured. None of these deduction rubbish thing. And it's a big schema. You have seen in the small screenshot before 100% of Foaf. This is what you're seeing in my screen. These are just the entities, not the relationships, just the entities in schema.org. There is a huge amount of entities, sub-entities, sub-entities, so classes and subclasses, for a lot of topics, all topics that Google cares about, like web pages, people, news, recipes, trips, schedules, and so on. It's a huge model. And inside each of these entities, there are many relationships. And these are just relationships for person. And you can see what the difference is compared to what we've seen in Foaf. You can say things like, I studied in a certain university, I've been awarded a prize, you can contact me in this way, you can tell me where I was born, where I died, you can say which gender I have, good luck with that. You can say if I am a doctor, professor, doctor honoris causa, and so on, which kind of membership I have, how much money I have in the bank, and so on. So there are plenty of things you can say. All these are relationships in this model. It's a huge effort, and the whole point of it is to be able to embed this kind of information inside HTML. You can also express this as RDF, RDFA, as we said, but the point is that in this way you can enrich pages. And this is why Google was very explicit, and Yahoo, they were very explicit in not starting from RDF, because they want to say this is an extension of HTML and microdata, or HTML and linked data, but this is not based on RDF. This is not a triple store. This is something that lives inside the HTML. Okay, that said, we can skip that. We can skip to Wikidata. Wikidata is the youngest of these three models, and it is a side project of the Wikimedia Foundation. The idea is that we can take Wikipedia, that is non-structured information, extract some of its semi-structured information, like names, numbers, and places, refine it, and then turn into structured information that then we can reuse in the Wikipedia pages for the info boxes. And Wikidata is already more or less bigger than schema.org, but in addition to schema.org, it has extra functionalities like multilingualism and interlinking. So while schema.org tries to describe things as precise as possible, what Wikidata tries to do is to link resources as much as possible. And all the properties, this is a very important thing, are first of all described as numbers. Those numbers as also labels. But for example, the property of having an occupation is P106. It's not occupation. Its occupation is just the informal English name for it, label for it. The real name is P106. And we can see an example here of Albert Einstein. This is Albert Einstein is a Q937. Albert Einstein is just a label that we commonly use, but this resource is called the Q397. This is an instance of a human. It has all these labels that you can see here and Wikipedia references about its citizenship, when it had certain citizenships and when other. This data in which units are, so this is just not a calendar, this is a Gregorian, not Julian, for example, calendar, and plenty of other information about it. And as you can see, this is important, but what is really cool is at the end, come on, the fact that they're linked to, here we go, hundreds of other similar resources in other projects, as VIAF authority files, IDs in the Vatican Library, in the Library of Brazil, you name it, it's there. And all these links are great when you're doing graph analysis, because all this Wikidata has a lot of, so first of all, in Wikidata, there are many entities, and each of these entities are deeply interconnected with the rest of the world. So it is a great point to understand what is what and what is available what. And from there, you can suck information from these other sources, integrate them, do a lot of interesting things. Okay, and now that's it.